Thank you very much. We've all had a long day and probably a long weekend. So some good news for you. There are two pieces of good news. First piece of good news is there isn't a single equation. There isn't. The only numbers in here are fake. So you can all relax and sit back, and this is going to be, up here. The second thing is I used to be in business, and when you are giving lectures to important business people, as academics, what we like to do is like to tell a story. And we like to talk for 45 minutes, and it's building up, and you give the answer at the end. And I mean, your students are actually all asleep long ago, but nonetheless, you think it's great because it's like a novel. Business people hate that. So the first slide of any presentation, in fact, this is the only thing you need to know from this talk. The first slide you ever give in any presentation to a team of business people gives the answer. Just give the answer up front. Then they can follow the talk, okay? Then they can know where you're headed. They insist on that. It's called the executive summary usually. It's the only bit they ever read if you ever write a report for them. So there you go. You can leave the rest blank. So here's what I'm going to say. Basically, and this is, really sort of anathema to the neural network community, but never mind. But really, a coherent theoretical framework is a nice idea. Just, sticking it into a network and hoping something is going to come out the other end is interesting, and it appears to work. But it's also interesting to try and understand why it might be working. In language processing, I think structural linguistics is an excellent candidate. And structural linguistics has been around for 100 years, which is slightly embarrassing. But I'm going to try and persuade you in the next 45 minutes that it's worth thinking about and worth looking at. Thirdly, an implication of that is, in my mind, language processing is probably like vision and chess. My expectation is that we will be able to make machines that have language competence and have high levels of language performance without insight and without intelligence. So sort of an anti-Turing. I mean, I think Turing was smarter than that, and the Turing test is not just about language performance and language competence. But essentially, I think there's a good chance we'll be able to create machines that are excellent at language, but there's nothing in there. And lastly, I think there's an idea that neural network processing is doing sign manipulation as a semiotic machine, which probably doesn't mean anything now, but will mean a little bit at the end. So that's quite long and complicated. This is the executive summary. If you're working in language processing using current techniques, I think they're probably going to work a lot better than even you think they are. So keep calm and carry on. All right, what do I mean by language processing? For my little corner, basically we're sort of trying to build a system for processing language. So we want to create data structures to represent linguistic units, say at the word, the phrase, or the sentence level. Create data structures that behave as if they've captured the meaning of linguistic units when manipulated with specific algorithms, and then fill those data structures with knowledge. And then go perform useful tasks with the system. So for us, it's about data structures that allow the machine to behave in a way analogous to the way in which humans manipulate meanings, and data structures then that are filled with appropriate language knowledge. So what are we going to do? We have 4 sections. I'm going to introduce briefly compositional distributional semantics, which is the area that we work most intensively in. I'm going to talk about anchor-packed trees and composition as contextualization. So that's the actual research that I've been involved with alongside Professor David Weir, Dr. Julie Weeds, and Dr. Thomas Kober. I'm then going to talk about what I think are the actual theoretical underpinnings, looking back to someone called Ferdinand Saussure and structural linguistics, and finally a brief page on the implications for language processing, the answer to which I've already given you. Okay, so what is compositional distributional semantics? Okay, starting from the end, semantics. Study of the representation and processing of meaning in language. So meanings of words, meanings of phrases, meanings of sentences. Distributional. So this is the idea that meaning is in some way based on the arrangement of those linguistic units in an utterance or a piece of text. So you've got a piece of text, and that text in some way tells you about the meaning of the pieces of text within that. Compositional, so that's the idea that we can take individual pieces of text, individual words, for example, word 1, word 2 with meaning 1, meaning 2, and we can use some process to combine those words together and create some kind of composite thing which then has a meaning of its own. And what you want to do, you want some kind of process that makes that composition to produce a meaning that is appropriate in the language. So the approach of distributional semantics basically comes out of work by people like Zelig Harris, John Firth in the 1950s. And if you read a distributional semantics paper, it will usually start with a couple of quotes and a reference back. And if you look at these quotes a little bit more carefully, Harris in 54, what did he say? He said, he went on a bit, but if A and B have some environments in common and some not, so he's saying if you've got word A and word B, and they seem to be generally surrounded by similar words, but some of them different, then we say they have different meanings. And the amount of meaning difference is corresponding roughly to the amount of difference in their environment. Firth was British, Harris was American, you can see the difference. Firth said, "You shall know a word by the company it keeps." Typical Brits, it sounds terribly profound and doesn't really mean anything. Then back into the 60s, words which are similar meaning occur in similar contexts. Schutz, Pedersen, 95, words with similar meanings will occur with similar neighbors if enough text material is available. You can see the starting appearance of data. 97, a representation that captures much of how words are used in natural context will capture much of what we mean by meaning. And Pantel, words that occur in the same context tend to have similar meanings. So you kind of get the idea. And sort of cutting to a chase, what we're generally assuming is the representation of word is determined by the context in which it occurs. So how do you build a typical distributional semantic representation? Well, you get a large corpus of documents. You gather some context. And what you think is context is kind of up to you, but it's typically, if you're looking at cat, it's typically the words around, domestic, small, furry. And maybe you'll look at grammatical dependencies, maybe you'll look at other things, but often you're just looking at the words around. And you do some process, and you process that into some data structure, typically vectors. It doesn't have to be vectors. That process can be, glove, word to vect. There's all sorts of different, maybe some deep learning thing, or maybe something that you're just counting the words around, doesn't really matter. And you turn that into some kind of representation which is intended to stand as a meaning representation for that word. So with those kinds of distributional semantic approaches, we've got a couple of words here. So on the left, we've got insect. And you've got a bunch of context in there. Some of that context will be brown, because insects are sometimes brown. Earth, because insects are sometimes talked about as having something to do with earth. Insects eat things or get eaten by things in sentences, so that's all there. On the right, worm. Okay, you get worms wriggle, worms burrow in the earth, all those things. But you also get computer worms, so maybe you have sentences with computer in there. So, okay, so how similar are the words insect and worm? Well, they're kind of similar. In the insects and worms are terribly similar, but computer worms aren't so similar. So, We can all write it down and see what we come up with, and experiments are done like that. But yeah, they're kind of similar to each other. So you want to have a representation of insect, you want to have a representation of worm, and when you ask the machine how similar they are, it should be able to come up with something that says, quite similar. So where does composition come in? Well, let's do that again, but now we have juicy and worm. So now we know more about this worm. Now we know it's a juicy worm, unlikely to be a computer worm. So we've got some kind of contextualization here. So if we take insect and we take juicy worm and we compose that into some new structure, goodness knows what that looks like, and we compare insect and juicy worm, we want to end up with something that's more similar than insect and worm. So that's kind of the challenge we're looking at here. So there's been various approaches. Your typical vector-based model of composition, back in the Stone Age, Mitchell and Lapata, 2008, 10, a bunch of papers since. Basically, word representations are directly derived from a corpus, either counting in the old days or some kind of method for predicting the words that are going to be around it. And lots of ways have been tried of composing these simple vectors. It's actually quite hard to beat naive operations such as adding the vectors together or multiplying them, intersecting them in some way. And that actually works reasonably well, irritatingly. But it's hard, intuitively there's a bit of a problem there because it's hard to capture interesting linguistic properties such as a credit card is not the same as card credit. But if you just add together a vector for credit and a vector for card and get this credit card thing, it can't capture the fact that there's non-commutativity here. The credit cards, we know that credit cards aren't the same as card credit. So works well, but rather wish it didn't. Non-vector-based models of composition, so people have tried to capture that linguistic complexity. So Baroni and Zepparelli, Ed Greffenstedt, before he decamped to DeepMind, sort of borrowed ideas from formal semantics. So recognizing that words are of different types. So an adjective is a function which maps to a noun to create a compound noun. So juicy acting on worm creates juicy worm. So an adjective is a matrix, a worm is a vector, and you get a juicy worm vector out of it. Some issues with the representation spaces of words, phrases, and sentences, not readily comparable, but maybe they shouldn't be comparable. Lots of parameters. Okay, so there's a couple of challenges in there. At the lexeme, at the single word level, so our insect and our worm, when we do these things, we get a continuous model of lexical meaning. So differences are on a continuum. And it works pretty well, just this very simple distributional model, and have been exploited successfully in a wide variety of contexts. And in fact, your average computer is better than your average person at estimating the difference in meaning between any random pair of words. By which I mean is your average computer will be closer to the mean score of a bunch of humans than your average human will be. So the computers are kind of better at saying which words are similar. So it's not a very exciting parlor game, but there we go. So that's good. But when we try this composition, we can see, firstly, how can we represent meaning-sensitive linguistic properties like non-commutativity, which the vector approaches don't manage. But in doing so, is there any way in which we can preserve the placing of words, phrases, and sentences in the same space? Because it's kind of nice if we can sort of hold language all within the same space and deal with sentences and deal with words and deal with phrases with kind of the same things. in doing so, should we preserve that placing, and if so, how? So here's an example. So floor, you kind of want floor to be similar to a third floor, a concrete floor, a wooden floor. These are all, you're wanting concrete floor and wooden floor to be very similar, whereas wooden movements, you want to be pretty different. That's all fine. But do I want wooden to be similar to wooden floor? Kind of, maybe. Do I want third to be similar to third floor? What do I do with I swept the floor, a complete sentence? So it's sort of this interesting question of what's comparable, and what do we mean when we're talking about comparability, similarity of these things, and how can we sort of put them in the same space and talk about them in that way? So what we want to try to do is to combine the simplicity and unity of these sort of simple vector approaches with the linguistic power of formal semantic non-vector approaches that are taking into account these linguistic properties. So anchor-back trees is our stab at that. What we make most use of here is, or a key use of here, is the idea of dependency relations. So for those without a linguistic background, congratulations, saved a lot of pain. If you think of any two words within a sentence, certain words will have a sort of a key relationship to each other. Many words will have no relationship to each other, but certain words will have a key relationship to each other. So cricket, ball, cricket has a relationship to ball. And the has a relationship to ball as well. It's the, ball, the, and cricket, ball. Ball and hit have a relationship to each other. Ball is the thing that's hitting something. Hit the castle wall, so hit and wall have a relationship. Stop me when I bore you. Castle and wall have a relationship, and so on. So it actually forms a little tree. So here I've actually plotted out a little tree where each node is each word there, and the line between them is a dependency grammatical relation. And there are nicely trained up analyzers that will parse things for you like that. So what we do is we sort of make use of that. We say, okay, these relationships we think are more useful than proximity relations. One is perhaps a substitute for the other, but let's focus on these key linguistic properties that we know are important. So what we do here is we get all of the sentences we can find with ball in them. We build a dependency, this little dependency tree for each of those sentences, and then we're going to superimpose all of them on top of each other. So this is 1, 2, 3. So we've seen ball 6 times here. And we've got 6 different dependency graphs, well, actually trees, one for each of the sentences we've seen. And what we're going to do is just mush them on top of each other and create what we call an anchor-pack tree. So here's ball. Here are the different relationships to possible grammatical relationships to different types of words. And then these are all the grammatical relationships that were in there in all of these sentences. So this anchor-pack tree, this ball, sort of captures the essence of all the times that we've seen ball in the sentence and the sentences around them. So if you look at that in a little bit more detail, here's our anchor-pack tree for cat, moved on from balls. And if you take the node that's responsible for cat, that just has cat in it, and we're looking here at things that we've seen modifying a cat. You've had small, you've had furry, you've had cross, you've had hungry, you've had tired, and so on and so forth. And you can just count how many times you've seen them. You can have some algorithm that's trying to predict how often you'll see each of those, and so forth. So what the APT is doing is storing facet. If we believe that context is distributional context is everything, we'll come back to that, then the APT here is storing facets of meaning. It's saying a cat, the cat you're seeing, so when you just see the word cat, the idea here is that what your brain's saying to itself is, oh, that might be furry, that might be cross, it might be hungry, it might be tired. You're just seeing cat on its own. You don't know more about that cat unless you're seeing other words around it. And as the sentence will be built up, you'll be learning more, you'll be contextualizing that cat. So one way I think about it is, so the APT is providing a representation that sort of describes the probability of seeing certain facets of meaning for a word in an utterance, in a sentence. So I sort of think of it sort of like a cloud of uncertainty. You see a word, you see a phrase, you're sort of trying to build the sentence around it, filling out the description of that cat. Okay, so this then is this is the clever bit. Now we've got cat and we've got poorly. So we've built the APT for cat, we've built the APT for poorly. Now what's quite nice is you can take these two tree structures and you can align them with each other. So basically, if you think about going back here, we have this alignment here. We have this known relationship between cat and a modifying adjective of cat. And here we've got a modifying adjective, poorly, and here you've got your cat. And you can imagine, poorly has been all sorts of other things. Poorly person, poorly child, poorly dog, poorly hamster. Get the picture. So this is the meaning of poorly, if you like, the representation of the meaning. So this is, you can have all sorts of poorly things. And this is a cat, the meaning of cat, which can be all sorts of things, strong, hungry, blah, 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 but including poorly. So what we're going to do is align the two trees on top of each other so that where the adjectival modification for cat would be, you put poorly and its tree, and where for poorly you've got the thing that it's modifying, you put cat and its tree. And the two trees then sort of combine on top of each other. And you can pick your favorite composition process. You can have a process which then basically mushes them together in some way, adds them together, or you can have a process that sort of intersects and strips away bits of tree. Or you can have something that's some combination of the two. But what you've then got is a new APT for poorly cat, which sort of describes the likelihood of seeing facets of meaning for the composed phrase. So now what you see is around poorly cat, you've got this sort of, you don't know what else you're going to see in the sentence, but you've sort of got predictions of what you're going to see, because it's not just a cat, it's a poorly cat. So that's the essence of the approach. So it has key data structures, these static stored APTs, which you create by, reading Wikipedia. Dependency structure for any sentence you want to produce or interpret. And then you can take that dependency structure, you can take that sentence, and you can compose together the elements to create an APT for the composed structure. So here, child cried, or child cried loudly, or an entire sentence or a piece of a sentence. So if you've got child cried, this structure represents three things. It represents child cried. It also represents this child. And it also represents this thing that cried. And in fact, you can go into any node, you can pin yourself on any node, and you've got a description of the sentence from the perspective of that node, even if the node doesn't actually have a word in it at the moment. So it's a single structure that's representing the sentence or the part sentence or the phrase of the word from every plausible aspect of that sentence. So to summarize that, composition here is a process of mutual disambiguation or contextualization. So it's no longer a cat, it's a poorly cat. This grammatical dependency, this use of syntactic dependencies, grammatical relations, allows you to capture different meanings that occur as a result of those grammatical relations. So credit card versus card credit. The representation of a sentence is simultaneously a representation of the sentence and of each word in the context, and of even the phrase within the context. So I think what's going on here is, if you're looking even at the representation of a dog, what you're looking at here is a representation of the incipient or anticipated sentence. So the reason why they all sit in the same space and have the same format, and you can compare directly to each other, is that they're all representations of a sentence or of an utterance. So the idea is that if it's a word or a phrase, the reason why they all sit in the same space is all of them are sort of sentences. And you just know more about the sentence when you see more of the sentence. Applications are the usual applications. Word sense induction, semantic relation discovery, sentence completion, language modeling, question answering, etc. Okay. So what's the problem with all of this? I mean, I think the biggest problem here is this stuff. Because, I mean, it's pretty wishy-washy. Distributional hypothesis, I mean, it's just, it's just words, right? It's just ideas. I mean, just comes out of nowhere, really. If you look at it a bit more carefully, there's sort of two weak ideas here and one strong idea. So what's the first weak one is it just says words that occur in the same linguistic context tend to have similar meanings. Fine, it's kind of unarguable. It's an idea. The second one is the more likely it is that words will be seen in the same context, the more similar these words are to each other. So it's kind of a substitutability idea. The strong version, which is the interesting one, and can be tied back to something theoretical, is this idea that the meaning of a word is determined purely by its linguistic distributional context. So that's a much stronger claim. It's one we've kind of been tacitly assuming, but it has some pretty significant implications if you work it through. And those weaker versions are sort of a retreat from the original ideas, which I think you can take back to Ferdinand Saussure at the beginning of the 20th century. Interesting guy, has been very influential in a bunch of different fields. Curiously, less influential in the one in which he did all his work, which was in linguistics, but still reasonably influential. And the distributional hypothesis type ideas are sort of a shadow of what Saussure originally proposed. So let's go back to what I said we were doing when we were doing language processing, and look at what someone like Saussure and his ideas can contribute to that. So we're trying to create data to represent linguistic units. And what Saussure was doing was trying to provide a coherent description of language. So outlining the structure of language, making a claim about what language was, describing the linguistic units and describing how they functioned, defining how meaning is represented, and determining what kind of knowledge is required to know a language, and what you need to do to learn that knowledge, so how to learn a language. So, I mean, he only came up with a sort of a bare outline of a theory, but if you have a consistent, coherent description of a language, its linguistic units, how meaning is represented, what kind of knowledge is required, and how to learn that language, then you have a cookbook for sticking it in a machine. And that's kind of what we need at the moment. So, okay, let's review some of Saussure's ideas. Structure and linguistic units. So what Saussure said is that and every linguist gets told this in the first lecture, and everyone kind of knows it, and no one kind of knows it. So what he said was language is purely a system of signs, a set of conventions we use to communicate ideas. And we're going to unpack that in a second. And signs, what's cool about signs is they're internally, in Saussure's model, is they're internally described with no external references, right? So a tree is a tree not because there's a thing out there with leaves. A tree is a tree because it is. It fits within language. In other words, you don't need to know anything about trees for you to talk about trees. And this is why I think about the sort of Blunkett problem or issue. So David Blunkett, blind most of his life, hugely successful politician, Home Secretary. His perceptual experience of the world is very, very different to most of ours. But he was and is capable of functioning at the highest level. So what his mental map of the world looks like is going to be very, very different to yours or mine. But that does not impede him in any way, and certainly not in his processing and understanding and use of language. So what Saussure said was, forget the thing it's referring to. Forget the tree. Forget Hillary Clinton. Forget Donald Trump if you can. That's not how language works. Language is this internal thing. So let's unpack that. So what is a sign? So sign is a tightly wrapped combination of a signifier, so CAT, cat, and an idea which is signified. So to put this in modern terms, you might say it's a combination of some surface feature and some embedding, some representation. That's it. And the sign is the linguistic unit of language. And that doesn't just mean it's a unit, it is language. Everything in language is operated through the manipulation of signs. And that includes grammatical properties and relations. So those dependency relations, they are linguistic, they are signs as well. Everything in language is signs. Okay? So the next thing it says is, and linguistic units signs are completely arbitrary. Now, when you first learn about the arbitrary nature of the sign, everybody thinks they know what that. Yeah, we're going to call a neutrino a neutrino, but we could have called it a foo or a bar or a baz. And, it doesn't matter, right? So that's arbitrary. So, and different languages call things different things. So it's kind of easy to understand that the signifier, the surface feature, is an arbitrary thing. We just all have to agree it's called a neutrino. But what's slightly more interesting is that the thing that's signified, the other half of the sign, is also completely arbitrary. So how we sort of divide up the semantic space is kind of entirely up to us. This is one of the reasons why translation is so hard. Okay, so let's take an example here with French. So in this little map here, you've got a river, maybe you call it a stream, a small river there, and you've got a big river there. And that small one there is called rivière, and that big one is called fleuve. So you say, fine, okay. So in French, stream is rivière, and river is fleuve. But that's not how the French carve it up, because they're French. A river or a stream is a rivière if it flows into another river. A fleuve is a fleuve if it flows into the sea. So the fleuve can be tiny, little stream flowing straight into the sea, that's a fleuve. A river can be huge, but if it flows into another river, it's a rivière, not a fleuve. I hope that's clear. I'll be testing you later. Here's another one. I'm sure some of you knows what this says, but at least the claim is this range of shades of blue in English is blue, and in Russian is two different colors. And this all, everyone seen Arrival? Great film. Is the one with the hexapods and the aliens? Yeah, cool film. So that's all about Sapir-Whorf hypothesis, which kind of comes off this stuff, where the idea is how you model the world with your language, then determines how you perceive the world. So there's been some experiments here that have claimed that the Russians are slower or faster, depending on what you do with the experiment, at doing things based on those two differences than Western people are. Because for the Russians, it's two different colors. For us, it's only one color. It's all terribly controversial in America. But you can see here the idea that for the Russians, there's two separate colors. For us, there's one separate color. We just divide up our color space differently. And these things can change over time. So here, cattle used to, the meaning of cattle used to be property. Then over time, because lots of people used to have animals as their property, the meaning of cattle became animals, because it's your property. And that was all animals. And now cattle means cows. So you've had the same word, but the way in which we've carved what it actually, the signified piece, what it means, has shifted over time. So both of these are completely arbitrary, both what we're calling things and what it is they're both arbitrary. So what's curious about Saussure's model is it's a computational model of language. It's a computational model of language about 25 years, well, 30 years before Turing. So, it's reading it is a fascinating experience because the poor man is trying to describe a computational model long before people have really thought about computational models. But what he says is, look, both signified and signified are purely differential entities. And he called them, they're defined by values, by computational results emanating from differential relations with other signs. In other words, you know that a cat is a cat through the fact that, what is a cat and what isn't a cat is defined by other things that it's similar to, but which aren't cats. So we all sort of agree what qualifies as a cat and what doesn't qualify as a cat, or what qualifies as cattle and what doesn't qualify as cattle. And then all the other things around it that sort of carve out the semantic space. So when cattle meant property, you didn't have other words around property that were other bits of property weren't there. But as cattle sort of came in and into bovines, other words moved in and occupied the semantic space that cattle used to occupy. So, so basically what he's saying is that we had that similarity engine. He's basically saying, look, that's the sort of thing that's going on here, so that computational values emanate from computational manipulations between these signs, between these representations. And he talked about values emanating from the system from two types of key comparison: between sequential neighbors in a sequence, so the stuff around in the sentence, and also between associative relations, exchangeable neighbors, so that we know, for example, when carving out that semantic space, that it's something to do with other things that you could kind of put in that sentence that would be almost right but not quite. And they're the other bits of the semantic space that are defining the bit in the middle, which is whatever the word actually is. And then there was a nice, how he got there, I don't know, but he then pointed out that these relations occur at succeeding levels, hence the structure. So at each level of a structure, one identifies the elements of language by the capacity to differentiate units of the level immediately above them. So that's easiest seen by looking at how we build letters up into a word. And then once you've built the letters up into a word, you imagine C-A-T-T-L. You can, we've seen so far, we've seen C-A-T-T-L. We don't have a word yet. If we wanted to predict the next letter, we'd have a pretty good stab, right? E. case anyone was wondering. And when we get CTATTLE, we've then created a word that then is at the next level of representation. So you can kind of see it, you can kind of see it with letters to words, that you've got a whole series of structure being built up as the word is built up. Once you get to the word, then it's a new unit. And you know about that unit because it differentiates. If you know it's cattle, you know it's not a deer. It's telling you about what other things are or are not. So at each level of structure, the elements of a language is, you know when you've reached that level of structure, if it's then, that thing is then capable of operating at the next level. So CATTL doesn't tell you anything useful. CATTLE tells you useful things at the next level. So I had here syntagmatic neighbors, cat stretched out in front of the fire. Then associative neighbors, we try just slipping one in. Can dog go in for cat? Absolutely. Can fox go in for cat? Well, probably not, except my wife's aunt had a pet fox. And the pet fox used to stretch out in front of the fire. So actually it happens. Cheetah, probably risky. But there was a great program, I never found it again, there was a great program about a guy who formed this relationship with a wild cheetah in South Africa. Has anyone seen it? Does anyone know where I can get it? Because it's a brilliant program. And they don't lie in front of a fire because it's South African, whatever. But they do lie down together, and boy, do cheetahs purr. And it's wonderful. And then towards the end, the cheetah gets killed, and the guy cries, and so do I every time. So, cheetahs kind of can stretch out in front of the fire. Just you've got to get to know them really well first. Right, well, there you go, see. So I wonder if it was that one. It wasn't, but another one, it wasn't that one, but it was a really wild cheetah. I mean, it was, it's not wild as in wild I was livid. It was a wild cheetah. It only hung out with this one guy, but yeah. Cheetahs, yeah. And tigers, Aspinall used to lie down with his tiger a lot. Unfortunately, they do have a tendency to eat you eventually. Anyway, you get the picture. So it's not quite straightforward, but that's the idea of what a cat is or isn't. Is sort of those are the boundaries. At least where stretching out in front of a fire is concerned. So what I want to get you is a slight vague intuition of understanding that language in this model, language is a total house of cards. You remember that I said you don't have to know anything about anything to know language. You don't have to know about trees, not what they actually are. You can be blind, deaf, and dumb and still be pretty good at language under this model, because what you know about trees is just down to its, what words you see around it and what other words, so flip one of these, you're in trouble. But it all knits together, and that is language. And for computer scientists, I mean, it may not be true, right? Probably isn't true. But it's brilliant, because I don't have to worry about senses or grounding or databases with facts in. I just have to feed it language. And if this is right, or a vaguely useful model, then it'll handle all the rest, particularly if I'm doing something that can manipulate signs. And what is a sign? A sign is a feature coupled to an embedding. And we know how to make couple features to embeddings. It's kind of, it's the only thing that neural nets can do, as far as I can see. So what Saussure said is, look, to know a language, all you need is a comprehensive inventory of the syntagmatics, so that's how words sit next to each other, and the associative relationships, which you derive from looking and seeing which ones are similar to other ones, between all the signs in the language. And if you suck all that up, you know the language. And you don't, and that allows us to talk about neutrinos. Hands up who's seen a neutrino, right? They're hard to see, okay? But we can still talk about them, right? We can have a discussion about them. Some people may know what they're talking about. There are real hints in the way in which we use language that tells us that it's a bit like maths. It's sort of this internal structure. I'm going to get mathematicians crossed by saying that, aren't I? Anyway, it doesn't matter. That exists just through its internal logic. Okay. So Saussure said something really nice. He said, look, in order to learn that sign system, which he called langue, because he was French, well, Swiss, same thing, you need exposure to a large corpus of individual utterances. He talked about speech. I'm talking about written word because computers, it's easier with written, which is called parole. So this is the next question. How do you get, it's a chicken and egg one. A language only works if you understand all of these relationships between each other, and this house of cards can be built up. But how do you build the house of cards up? Kind of tricky. And he basically said, langue, that house of cards, is a social product. You and I don't have much choice about, there's YOLO, of course, which is kind of new, but you as an individual don't have much choice about the langue side of language. It's just what we all, you hear a lot of sentences and you build your langue app. Maybe if you use YOLO a lot, it becomes a thing. But essentially, the formal product, the langue, is a system of forms. It's a set of signs, including grammatical facts. It's a system that derives value from those differential relations. It's that house of cards. It's a social product that you learn. It's something we all share as a community from exposure to utterances. Parole, which is stuff like I'm doing, utterances that are made possible by the language. Utterances in the language, they're expressions formed from the application of this static thing we've got in our heads. So I'm basically manipulating signs, putting them together, shoving them out. You're decoding that. All right, so punchline, such that it is that the APT stuff I was showing you earlier is very Saussurean. Wasn't initially set out to be. It's kind of backed into it. And of the four of us who work on it, I'm the only one who's really interested in this. But there we go. It's basically a structural linguistic model. So you remember the static stores of APTs? That's your house of cards. That's your langue. So the APTs are essentially a social product. The way I build them is I just feed the computer a load of sentences. The signifier, we've got the word child, and then this APT structure is the signified, built of these grammatical relations tying together possibilities of words that might be there. And the syntagmatic neighbors all sit within that structure. The combination of a sentence dependency in a sentence, and then the composed APT I use when I put these things together to compose a phrase or a sentence, that's all parole. And I can use SIM algorithms to generate my contextual associative neighbors, to work out my semantic space, other algorithms to characterize associate relationships. And that structure then is a representation of the composed, here, crying child. How am I doing? 46 minutes. Okay, so we're done. So what am I suggesting? A coherent theoretical framework is a nice idea. Having some kind of vague idea or understanding of why the language processing you're doing might be working, it feels better. Structural linguistics, for me, is an excellent candidate for that. It's simple, and the linguistic units is asked for. Manipulation of signs is completely compatible with network processing, with neural network processing. It looks just like it. Meaning representation is computational and accessible, and the type of knowledge you require is simple. You just have to read text. It's basically unsupervised learning, completely unsupervised learning. And it doesn't require any external reference, any sensory input, any grounding, any translations to other schemas. I don't have to stuff it in a database or knowledge base or apply logic or any of that stuff. I just do language. As I said, for me, the implication is the language processing, I think, might be like vision and chess. If this was right, you could probably create a very effective sign processor that can do language without any insight into what's out there, or frankly, any general intelligence. And I think what are these neural networks doing? One possibility is obviously they're not just doing pattern recognition; that they're perhaps doing this kind of semiotic processing, this sign manipulation. That's it. Thank you very much indeed.
It's very refreshing to see that linguistic structure is making its way back into natural language processing. So thank you very much for that. Now, my question is, if we have no need for external reference, how do you deal with ambiguity in dependency parsing? For example, if you have the sentence, scientists watch whales from space, how do you do the dependency tree then? How do you deal with these kind of situations where you actually need the context to parse efficiently?
Yeah. I'm going to go even more hand-wavy here. What's cool and interesting and surprising is that, a grammatical dependency is this thing that we've just come up with, right? Which seems to work, but we just came up with it. When I say that all grammatical relationships are signs in exactly the same way, they are signs exactly like the sign for cat. Even though in English a grammatical dependency doesn't typically have a surface signifier, doesn't have CAT. There's the apostrophe S you get for that grammatical dependency, but that's about it in English. So we don't see them as signs particularly, but they are signs. So I guess what I'm saying is that you can come up with they can be emergent in the same way that all of these signs are emergent. So it's not that we have to come up with a parser that parses them for the machine, and then the machine can do the decoding. Sometimes the parser gets it wrong, and what does it do then? Or it's ambiguous. It's all within the same structure. So that question is the same as the question when you get an ambiguous word in a sentence. And it'll be ambiguous unless there's enough to decontextualize it. In just the same way, if you just see the word worm, yeah, it's ambiguous. So you have this slightly more indeterminate representation until you know more. And I expect if we come up with a tricky sentence that is hard to parse grammatically, you've got the same thing going on inside that just have multiple possibilities. I'm sorry, I know that's a bit hand-wavy, but I kind of think it's a good answer. But one of my PhD students is definitely not allowed to ask a question.
This is a bit of a cheeky one. I'm sorry about that. So I was thinking, how much of this thinking that language is its own self-contained system and you don't need anything else outside of language. Obviously, the Saussure came up with this a long time ago. They didn't have computers. But in our day and age, how much do we genuinely believe that? Can you like really know what a cat is without having touched one?
I am almost the only person, as far as I'm aware, who genuinely believes it.
I'm thinking we do that just because it's really difficult computationally to put in tactile feedback and visual feedback. So it's very, very easy to go and download Wikipedia, and it fits within someone's framework. But I'm not convinced that when I build distributional models purely on text, I do it because I subscribe to the philosophical foundations. I do it because that's all I know how to code up.
Nobody else apart from me believes it. There are huge speech, there was a huge one a few years ago at ACL where someone had a wonderful speech about how you had to be grounded. I am the only one who believes it. But, I still think it's right.
It's possible I have to ask.
I think we can take one or two more questions.
Okay.
Thank you very much for your speech, for your presentation.
Thank you,
I was wondering how you compare APTs with word-to-vec, and maybe a word-to-vec that's trained on words that also contain their types. So, I don't know, beautiful adjective, to-do verb, and so on and so forth. How would you compare APTs and word-to-vec that was trained that way?
So again, I'm sorry.
How would you compare the APTs that you just shown us with a word-to-vec model trained in a way where words and the type of words associated with it are...
Yeah, you can do dependency-based word-to-vecs, absolutely. Yeah, we use those. I guess the difference with APTs and the difference between the sort of APT type approach and any of these other approaches is that we're caring about the form of the embedded representation. So that allows us. So with a word-to-vec or something, you've got 200-dimensional vector or whatever. You can't say, okay, this one here in my dog is the equivalent of this one over here in my hungry. So with the APTs, you have a method, you have a principled method of composition, and each node in it, which would be equivalent of you can vectorize trees, right? So any of these trees can be written as a vector. Each piece of the embedded has a linguistic meaning that a word-to-vec type thing doesn't. Now, I'm not saying that's necessary. I'm actually kind of saying the word-to-vec type approaches, handle all the embeddings themselves, and provided we solve backprop and all the rest of it, then, these things are arbitrary. So how the computer wants to organize itself ends up not being something I have to worry about, which is great, because that's how we do end-to-end neural networks. But at least for now, while I'm thinking about it, we sort of do APTs, and that then allows us to actually do these things ourselves. So we can do manipulations in the middle of that end-to-end thing and come out with intermediate results that have some, that work. But yeah, ultimately, you can dispense with all of that. So, maybe you can dispense with the APT approach. It's kind of what I'm saying, is the neural network approach looks great. Because all of the neural net, even if you're just dealing with these with words, this, the underlying theory here suggests that it's going to work.
Any final question?
I was just wondering if you could say something about what the process of discovering high-level concepts and reasoning about them might look like under this model of language.
Yeah. No idea. It's really, really depressing. You take out a linguistic book on semantics, right? And think, boy, we've got a tremendous, we're doing some tremendous stuff. And you realize we've got about halfway through chapter 1. And that's really depressing. Still, that means, you know, we've got a lifetime, you know, no problem with our careers. Plenty to go for. Thank you.